The governor of California has locked down the state. The mayor of Los Angeles has locked down the city. And the question is it going to do any good? Or more precisely, what effect will it have? Well, to answer that question, I'm going to use a little simulator that I created for the biophysics class that I'm teaching at my university. Now, before I get into the details of the little simulator, I have to emphasize that I am not an epidemiologist, nor am I a physician. My doctorate is in theoretical physics. So everything that I say is suspect. Right? With those disclaimers, let's proceed. All right, so the mathematics of the outbreak is pretty straightforward, and if you know how to code, it's a straightforward coding task, and so I did that last week. And I gave an assignment to my students, and I'm now going to use that simulator that I created. So let's first ask ourselves, what happens if we do nothing? So we're interested in what's going to happen in California. So let's go ahead and select the population of California. Let's take a guess that there were 100 people infected on March 1st. Okay, so we're going to assume the death rate is 2%. The average virus contacts per day per person, we're going to assume that's 5. And when a person comes into contact with another infected person, we're going to assume that the probability is 3% that they get infected. The average number of days between infection and recovery is assumed to be 14, and the average number of days between infection and death, I'm going to say it's 7. All right, so we're going to simulate what happens for the next year, and if the outbreak ends before that year, the simulation will end when the outbreak ends. I'm going to, at this point, assume there's no lockdown, and I'm going to assume that the virus is not affected by temperature and humidity. So I'm going to set that to no. All right, so click Simulate, and this is what happens. It doesn't look good. Deaths, 773,000, 2% of the population. 73% of the population gets infected. The peak infection rate, that's a problem. The reason that's a problem is that there are only, at the current time, about capacity for 10,000 patients, extra patients. So there's a surplus capacity for 10,000 patients right now. And if we assume that, say, 5% of these infected people need hospitalization, that's going to be a problem, because 5% of 800,000 is going to be what? 40,000, if I did the math right. 40,000 per day is not going to make it, because if we have 10,000 extra beds, only 10,000 extra beds, and we assume that the occupants of these beds stay in them for about 10 days, then that's going to be about 1,000 beds available per day. And we need 40 times that. All right, well, what happens if we change our behavior and we reduce our interactions with people? That is, we increase our social distancing, so that instead of encountering 5 people per day that might have the virus, we encounter 3. Let's change that to 3. And this would be our new normal. This would have to be our new normal. It would have to be the result of online education, telecommuting, people spreading out during sporting events, limiting the size of the crowd at sporting events, and so on. And let's see what effect that would have. Click simulate. All right, looks like the outbreak continues beyond a year, so it stretches it out a little. Let's try 1,000 days. And unfortunately, this thing was coded for not for efficiency, but here we go. So April 5th is the peak of next year. April 5th of next year is the peak. And let's take a look at the deaths. Not much improvement. The peak infection rate is down substantially. In fact, I was wrong. This was 770,000. So there was substantial improvement, about half a million. Take that back. And this was 800,000, and it's now 100,000, which means we need about 5,000 hospitalizations per day, and our current capacity is 1,000 per day, and it's not inconceivable that could be multiplied by 5, but it would be a stretch. Well, what else can we do? Well, we can introduce a lockdown. So let's have a lockdown. I'll turn the lockdown on. And let's make it a 14-day lockdown. Let's make it start today, today's date. And let's make it a perfect lockdown. Now, I know that's a ridiculous assumption, that the lockdown's not going to be perfect because of at least 3 things. Number one, people are going to be going to the grocery store and encountering other people. They're going to be going to the pharmacy and encountering other people, and so on. Number 2, we have this large homeless population, which isn't really going to be locked down. Number 3 is the borders are not closed. So the assumption of 100% a perfect lockdown is suspect. It's completely unrealistic. But let's suppose that we had that. What would happen? Waiting. Okay, it's done. Wow, it completely solves the problem. Look at the deaths. Only 250, essentially 0%. It's so small, it's approximately 0. Nobody gets infected. The infection rate, the peak infection rate is 36 per day. 5% of that is like 2 people a day. We wouldn't even notice it. But this is a completely unrealistic assumption. Let's try a realistic assumption and see what happens. And by the way, notice that the peak is on the 18th. In other words, it's already peaked, and it's just downhill from the day that the lockdown was instituted. All right, so let's go with a realistic assumption. The most optimistic, realistic lockdown would be that we're reducing contacts by 80% instead of 100%. So let's try that. That's the most optimistic scenario we could possibly assume, and I think that's probably unrealistic, but it's the best we could possibly hope for. Let's see what that does. Waiting. All right. The peak is now August 13th. We still have a high hospitalization rate. We still need 5,000 beds a day. And we still have pretty much the same number of dead. Just looks like it's about 3,000 less. The only gain is this. August 13th. Remember what it was before. Let's just go back to what it was before. I'll just turn this off so there's no lockdown. Let's look at the date. Waiting. All right. April 5th to August. That's a substantial amount of time. What is that? That's 4 months. So you get 4 months to prepare, 4 months to develop a vaccine, 4 months to pray, and that's the benefit of the lockdown. 4 additional months. So, is this simulation correct? Well, it's possible that it's an error. Is there any reason to believe that it might be correct? Well, let's go back to the case where we've done absolutely nothing. And let's look at the doubling rate. So here's 1,000 on the 17th day, March 17th. And let's see how long it takes to get to about 2,000 on the 22nd. So that's about 1, 2, 3, 4, 5 days, maybe 5.5 days. So the doubling time is about 5 to 5.5 days. Now, is that a reasonable doubling time? Well, let's take a look at this paper here. It's from China. It's published in the New England Journal of Medicine. And they claim that the doubling time is about 7.4 days. Their confidence interval is between 5.3 and 19 days, which means they think there's about a 2.5% chance that it's less than 5.3 and a 2.5% chance that it's greater than 19. Looks like their R0 is 2.2. Is that okay? So than they are. Their belief in their data shows that the COVID-19 virus has a doubling time that's faster than what we've got. So we're being a little conservative. Let's take a look at somebody else's estimates. Here's a paper that says, or an article that says that the coronavirus is spreading faster than the World Health Organization estimate. Let's take a look. They are estimating R0 to be 2.79. What's R0? R0 is the number of patients or the number of people infected per infectee. Directly infected per infectee. And their number is about 2.8. And the WHO number is between 1.4 and 2.5. Now, is there a way to relate R0 to doubling time? Well, let's take a look at this paper right here. And I'll have a link to all these references below. But in this paper, they have a nice little chart, and it's a relationship between R0 and the doubling time. And let's blow that chart up. And it looks like if we take that 2.79 figure, it would be out here somewhere. And it looks like that would correspond to a doubling time of 2 days. So far, we've seen one paper that seems to be implying that the doubling time is 7.4 days, and another paper that seems to be implying that the doubling time, if this is correct, is very rapid, 2 days. Well, let's look at the actual data and see what the data says the doubling time is. So let's look at this yellow growing curve, and let's look at about March 15th. And the number here is 82,000, 81.7 thousand infections other than China. And let's look at it 5 days later on the 20th, which is today, and the 82,000 becomes 164,000, which is a factor of 2 in 5 days. So the doubling time, based on the actual data, seems to be closer to our little simulation of 5 days. So I'm confident that that's a reasonable guess for the simulation. All right, so the simulation might not be total nonsense. All right, so what is the takeaway from all of this? I would say that the takeaway is that we should try to get as close to a perfect lockdown as we can, to give us as much time as we can. And in that time, we need to develop some sort of alternative method of dealing with this. Because if we don't, we have to deal with the large number of deaths, which in that case was 270,000 deaths in California alone. And let's close by taking a look at what happens to the world. So let's take the world's population. Let's assume there are about 80,000 people infected in the world. These are not the actual confirmed diagnoses. These are assumptions that we're assuming that the diagnoses are just a small fraction of the actual number of people who are infected. So we're going to say it's about 80,000 people on March the 1st. We're going to say we're going to do nothing, and we're going to say the typical number of contacts is 5. And all the other assumptions remain the same. I'm not going to have any kind of lockdown. I'm not going to have any seasonal adjustment for humidity. And we're just going to do the simulation. Here we go. All right, doesn't look good. Worldwide, 147 million dead. I don't know what to say. But it's exactly what you'd expect. If the virus went worldwide and has a 2% death rate, that 2% of the people would die. And that seems to be exactly what the simulation is saying. So on that somber note, if you have any suggestions on how we might proceed, please put them in the comments below. I should also mention that this little simulator is available for you. It's very simple. It runs on JavaScript. It runs in your browser. It's harmless to you. So I'll put the link where you can get it if you're interested. Take care and be safe.